Komið þið sæl. Ég ætla að fjalla örstutt doktorsstyrki Vísindagarða, en Vísindagarðar styrkja árlega 6 doktorsnema samtals 36 milljónir króna. Það eru sem sé 2 kandídatar sem hljóta styrkin við hverja úthlutun og þeir njóta styrksins til 3 ára hvor. Við val á verkefnum horft til rannsóknarverkefna sem eru í samhljómi við stefnu Vísindagarða. Það er að segja verkefni sem hafa mikla möguleika til hagnýtingar, auk þess sem verkefni á sviði lífvísinda, tækni og skapandi greina njóta ákveðins forgangs. Umsóknir eru metnar af fagráði og eins og aðrar umsóknir í doktorsjóði háskólans, þá þar farið eftir faglegum viðmiðum vísindanefndar háskólaráðs. Þetta samstarfi háskólan hefur staðið yfir síðan 2021 og það eru 10 nemendur sem hafa notið stuðningsins síðan þá. Þetta mikilvægur stuðningur við Háskóla Íslands og vísindastarf á Íslandi og styrkir Vísindagarða í sessi sem svona tengipunkt atvinnulífs, nýsköpunar og rannsókna. Við slóum á þráðinn til Vyshnav Mohan, en hann hlaut doktorsstyrk Vísindagarða árið 2024 og að vinna sitt verkefni við raunvísindadeild undir handleiðslu Lárusar Thorlacius, prófessors í kennilegri eðlisfræði. Vyshnav, do you hear me?
Yes, I can hear you.
Could you tell us can you try and explain what your research is about?
Yeah, so the whole program is called quantum gravity, and let me explain what that means. So one of the biggest breakthroughs that we had in the last century was the discovery of quantum mechanics. So we all of a sudden discovered that at very small length scales, the physics that we knew was just completely different. And now we call those laws collectively as quantum mechanics. And around the same time, we also discovered the laws of gravitation. Einstein came up with this theory of general relativity, and he discovered a new set of laws, and then this made more predictions. But we quickly realized that these 2 theories are not compatible with each other. And that means that we don't know how gravity works at very small length scales. And this is in stark contrast to every other force that we know of. For instance, if you look at electromagnetic force or strong force or weak force, we can make them compatible with quantum mechanics. So we know how they work at very small length scales. And that has immediately led to a lot of predictions, and we could verify all of that. But somehow gravity does not fit into this paradigm. There's something really different about gravity. And over the last, for a lot of time, we thought about this. Is there something wrong with our calculations? Do we have to fix quantum mechanics? But in the last few decades, we have realized that gravity might be not what we thought it was. And the current idea is that gravity might be an emergent object. It might not be a fundamental force after all. An example where you can see such an emergence is thermodynamics. So imagine you have a box of gas, and the things that we can see the gas to have is its temperature, pressure, volume, and so on. But we know that these are not fundamental objects because the gas at the end of the day is made out of atoms, and an atom doesn't have a temperature. It's only a collection of atoms that has temperature, pressure, volume, and so on. And it's an emergent property when we look at the collection of atoms that's when we see these things emerge. So what if gravity is exactly the same thing? And in fact, this is not a simple analogy. We can actually see that gravitational equations of motion are precisely like thermodynamic equations of motion. And my whole program thing that I'm working on is to kind of make this more precise. What are the atoms of gravity? How do you find those fine-grained objects from which gravity can emerge? And there are various concrete realizations of this. One particular idea is called the holographic principle, which I can get to if you have questions.
Yeah. I mean, these are very fundamental questions that you're dealing with. But we read in the newspapers, we read about quantum computers or quantum batteries. Do you see your research having any practical applications?
I mean, yes, I was thinking of this too. So recently, is there a way to kind of make this more precise? But yes, so as you have said, these questions are very fundamental, right? Gravity is a very fundamental object. And what makes gravity very important is that the moment you have matter fields, the moment you have matter in your universe, gravity is switched on. It's very different from electromagnetic force, right? Because you have to have charge for it to interact with electromagnetic field. But the moment you have matter, any kind of matter, gravity is there. So for anything that you really do at a very small length scale, these kind of gravitational interactions are important. And a precise example is this quantum computers, because in these quantum computers, what you do is you build these qubits, right? And these are bits, but they are in quantum superpositions. I'm assuming that you kind of know what these words are, but still, there's a way so you use quantum mechanics to build these bits. But an important question is, if we don't know how gravity works at these length scales, can it go and destroy this information? Mm-hmm. Can it kind of negatively impact the information that we are storing in, or at least theoretically storing in these days, because we don't have a big quantum computer, right? Mm-hmm. We are always assuming our things to work in the future. But if we ever want to make a really small qubit in the future, there might be gravitational interactions that could just go and spoil our information storage mechanism that we have built, because we don't know how gravity works in those length scales. Mm-hmm. So there could be implications, and it's precisely because gravity is a very fundamental object, and that we cannot just switch off gravity. Gravity is always there whenever we have matter. So so it is going to be important for these kind of objects and observations.
Mm-hmm. And I guess with fundamental research like this, also you can never really know at this time what the implications will be.
Exactly. I mean, the famous example is Einstein's theory of general relativity, which we are building on. So when Einstein came up with this theory, all he wanted to do was to make the gravity theory that we knew at that time consistent with some of the other theories that we knew. And it immediately gave us, physics for GPS and all of that kind of sophisticated stuff that we use now. So, and I'm pretty sure he did not know about GPS at that time. It's one of those little things where you can't predict, but you know for a fact that this is super important because it's a thing that we cannot just switch off, right? It's as important as that. Yeah.
Okay. Yeah. Great, Vyshnav. Thank you so much for giving us your time, and good luck with the rest of your research.
Thank you.
Þá þakkum við bara fyrir okkur.